Hello everyone. In this problem, we are given three input arrays. The first array contains the start time of a job, the second array contains the end time of a job, and the third array contains the profit of the job acquired during that interval. This sounds like an excellent way to see what jobs provide what profit. Prioritization. So, yes, our task is to return the maximum profit such that there are no two overlapping time slots for different jobs. The constraints are huge. First things first, the start time, the end time, and the profit array will be of the same size. Duh, obvious. So, we are not expecting any invalid input, and the minimum size of each array can be 1, and the maximum size can be up to 50,000 elements. The start time and the end time can range from 1 to 10 raised to 9, and the profit can range from 1 to 10,000. Since the start time and end time and profit have to be in a batch, so they cannot be separated. Any change that we make in one will have to result in a change in all three. Now, because this is an array question, we have some standard questions to ask. Will the arrays be sorted? And no, the arrays are not sorted. None of them are sorted. They can also be overlapping, like the start times and the end times can overlap. They are just going to be as jumbled up and messy as at least my calendar. Can there be duplicate start times or end times? Yes, there can be duplicate start times and end times, which means there could be two time slots starting at 1 and one of them ending at 2 and the other one ending at 3. Now, let's look at the approach. We will use a combination of two methods. First is a binary search to look for the index of the start, which is coming after the current end time. This process is key here to solving the problem. We will look into this later once we are trying to solve the problem. The second approach is to solve the problem using the greedy method, which means it is the best possible approach in this current iteration. Now, let's take the start time as 1, 2, 3, 4, and 6. The corresponding end times will be 3, 5, 10, 6, and 9, and the profit will be 20, 20, 100, 70, and 60. Our task is to return the maximum profit such that there are no overlapping intervals. To do this, we need the start time or the end time to be sorted because we will be either finding the start time or the end time for finding the current index. If we sort through the sorted array, it's easier to find the indices because binary search takes log n time versus the linear search where we have to go through each element every time. So yes, in our case, we will start with sorting the start time. In this problem, it is already sorted, so we don't have to do much about it. So we check with the end time 9. Is there any start time which starts after 9? So we have no start time that starts after 9. So the profit till now will be 60. So that will be the first profit that we have, which is 60. Then we go to our next elements, which are 4 and 6. So we try to check if we have anything after 6 as our start time. So we do have 6 as our start time, in which case we will consider that last element, which was 60. And we will add the current value, which is 70. So the total will be 130. We again go towards the next, which is 10. We have no start time, which is after 10. So the current profit till this iteration is 100. But the maximum profit that we have so far is 130. So we discard the 100 and instead use 130 as the profit with the start time 3. Go to the next time slot, which is 2 to 5, and the profit for that one is 20. We try to find a start time after 5, which is going to be 6. And the profit up until that index was 60. So we add 60 plus 20, which is going to be 80, but that is also less than 130. So we just choose 130 to proceed further. So the total interval from 2 to 10, we have the maximum profit that can go up to 130 so far. Now we come to the last interval, which is 1 to 3, and the profit is 20. We have to find a start time which is after 3 and consider the profit of those intervals. So for example, we have one interval which is from 3 to 10 and the profit is 100. So if we add that, 20 plus 100 will be 120. Okay, so that is one option that we have. The second one that we have is 4 to 6 and plus 6 to 9. So if we consider the start time at 4, which we have already calculated, which is till 130 as you can see. So if we add 130 plus 20, it will be 150. So out of 150 and 120, 150 will be the maximum, obviously. And so the total profit that we reach without having any overlapping intervals will be 150 for this problem. And we will just return the maximum profit, which we have obtained as 150 by iterating throughout the array. One thing to note is this problem could also be solved by dynamic programming. If you guys don't know what dynamic programming is, I'm also new to it, but it's a concept where we can break a problem into multiple smaller portions and we use recursion to find the answer. So it keeps calling itself till we come to the last point where we can go no further. I have also added some links in the description below if you want to check more about recursion. I'll also try to make another video about that. And now, coming back to the problem, let's look at the code to see how this is done. First, we form a list of tuples of triplets to keep the pairs of the time intervals and the profits together. Then we sort them according to our start time. We do this to make the search easier when we are trying to find an index that comes right after the end index of the current iteration. We then make a list that contains maximum profit at each iteration. We store the last value of the last time slot in our list of tuples just as the goodwill that this is at least the one job that we can get done and that can act as the maximum profit right now. We are choosing this last element of profit as our maximum profit because we are starting from the end of the list to iterate through the array. Okay, so now coming to the iteration, we already have the last value. So the first iteration is already done. We stored it. So we start from the second to the last and go all the way to the first element. So in each iteration, we are first trying to find the start index that is just coming after the current end index. Once we find the index, we look for a value in our maximum profit array for that index. Mostly if we have not encountered that start time before, the profit would probably be 0. It is to check what is the maximum profit for that given index. If the index is not present in the list, we just return 0. The next thing to do is add the current interval's profit to whatever profit we found at the index. We then compare it with the maximum profit we had in the last iteration and then choose the one which is having the maximum value right now. This will give us the maximum value up until that index. We use the binary search to find the index. In Python, it can be done easily using the bisect left function where you just try to give the start list and the end time of the current iteration. It will try to find the next start time. This can also be implemented using a simple binary search function where the left pointer is at the start of the list and the right pointer is at the end of the list. The target element is the end of the current iteration. We then calculate the midpoint. And if the element at the midpoint is greater than or equal to the target element, the right point will be midpoint minus 1. If it was less than the target element, the left pointer will be midpoint plus 1. And we keep doing that till left becomes greater than right. And if it does, we just return the left pointer. This will provide us with the element on just the right side of the end time. If there is no start time on the right side, it will return the index after the last element, which will lead us nowhere. The maximum profit will be accumulated till we come to the beginning of the list. So the maximum profit will be max profit of 0 and we just return that. Okay, so now the output for some of the test cases look like this. Coming to the time complexity, the making of the tuple to collect the triplets will be O of n. The sorting will be n log n. Making an empty greedy array list will be O of n. The outer loop will be O of n. And finding the index in each loop is log n. Because we use binary search, so that will be n log n. If we combine the two, we get this. O of n plus O of n log n plus O of n plus O of n log n. If we remove all constants, we just take the maximum value, and hence the time complexity will be O of n log n. The space complexity is also dependent on the input size, as the size of our calculating max profit array is dependent on that. So the space complexity will be O of n. Okay, this problem was tough. It took me loads of time and a couple of iterations to actually understand what is going on with this problem. Do you think you can solve this problem using dynamic programming as I mentioned earlier? Please let me know in the comments below how you do it. And as I said, I'm not that good with the concepts like recursion and dynamic programming, so that will be coming later. I have links to similar problems in the description below, and if you found this video useful, please like my video and subscribe to my channel for more videos like this. Thank you guys. Bye.